In this question, we're given a piecewise function, meaning the function is built from two different rules, and we must decide whether there's a discontinuity. A discontinuity is a gap, a hole, or a jump in the graph. Look at the parts separately. The cosine part is a smooth wave and is continuous. The other part is a straight line and is also continuous. So the only place a problem could happen is where the two pieces meet, at x equals pi over 2. Now test that join. Take the right-hand limit using the cosine piece and the left-hand limit using the line piece. If those two values match, there's no gap and no discontinuity. If they differ, there is a discontinuity. In this case, both limits are 0, and the function's value at x equals pi over 2 is also 0. Everything matches, so there is no discontinuity. The function is continuous everywhere. In this question, we're asked to do the derivative, so we follow our three-step game plan. Step 1, split up. We split at plus and minus signs that are not inside parentheses, fractions, roots, or powers. So here there's no split up because the plus is inside a parentheses. Step 2, set up. Here we build the structure for differentiating. Important, we're not differentiating yet. We're just building the structure, using the table from top to bottom. We can see we have two parts, each with an x, so we use this structure. Then we see we also have an x in the exponent, so we use this structure. The last step is differentiate. We only differentiate the parts with the d dx. These are simple functions, so we can use the circle trick to differentiate quickly, simplify the answer wherever we can, and we're done. Watch the full differentiation game plan video on our channel. In this question, we're asked to find dy over dx, which means we need to differentiate. We'll follow our usual game plan for differentiation. If you haven't watched the game plan video on our channel, do that first. It'll save you a lot of tears. Step 1, split up. Split at plus and minus signs that are not inside fractions, brackets, roots, or exponents. Here there's nothing to split. Step 2, set up. Use the table to build the structure. Remember, we're not differentiating yet. We're just setting up the structure for differentiation. We can see we have two parts with an x in a division, so we use the quotient structure. Step 3, differentiate. Use the cupcake method to separate simple from composite functions. We treat them differently. In the numerator, we have a sine function that's composite because its input isn't just a plain x, so we apply the chain rule. The rest are simple functions we can handle with the circle trick. Then simplify and you're done. Here we need to determine dx, which means we're going to differentiate. We start with our usual game plan, split up at plus and minus signs that are not inside brackets, fractions, roots, or exponents. Here the plus is inside a root, so we can't split. Step 2, set up the structure for differentiation. We only have one x, so using our table we see there's no special structure needed, no product or quotient. Step 3, differentiate. Use the cupcake method to decide whether it's a simple or a composite function, because we handle them differently. A root can be written as a fractional exponent, and when a bracket with a multi-term expression is raised to a power, it's always composite, so we must use the chain rule. Using the chain rule, we get the result. Then differentiate the inside with the usual circle trick. Simplify. Remember to move the negative exponent to the denominator. And if it's a fraction, rewrite it as a root. And we're done. In this problem, they ask us to find dy over dx, which means differentiation. Remember your notation. dy is on top, so we want y as the subject before differentiating. Right away, we can see normal algebra won't isolate y, so we use implicit differentiation. We differentiate both sides of the equation. Follow the usual game plan. Split up. On the left, we can split at the plus and minus signs. Step 2, set up. Here it's important to treat y as if it were an x. We can see the second term is a product, so we'll use that structure. Step 3, differentiate. With implicit differentiation, you must remember that y hides an x, so we always treat it as a composite, a cupcake with a hidden center, so we always apply the chain rule to any y. After that, just manipulate the equation to get dy over dx alone, and you're done. When they ask for f prime of x from the definition, we use the first principles limit. There are two ingredients we need, f of x and f of x plus h. We already have f of x from the question. To get f of x plus h, replace every x with x plus h. Nothing else changes. Now substitute both into the first principles formula. Use brackets when you plug in so you don't make sign mistakes. Then simplify everything you can. For the final move, factor an h out of the numerator so that you can cancel the h in the denominator. Once h is canceled, you can safely take the limit as h goes to 0 without a math error. That gives you f prime of x done. In this question, we need the slope of the tangent line to the function f at x equals 1. Remember, to get the slope at a specific point, we always differentiate the function and then substitute that x value into the derivative. That gives the slope at that point, the slope of the tangent. We have a natural log function, which I first think of as a log with base e. Now we can differentiate. Step 1, split up. There's nothing to split. Step 2, set up. There is only one x, so no special structure is needed. Step 3, differentiate. Decide whether the function is simple or composite, because we handle them differently. If the log's input is just x, it's simple. If anything other than a plain x appears in the input, it's composite, and we must use the chain rule. After applying the chain rule, simplify, then substitute x equals 1 to get the slope of the tangent at x equals 1. In this question, a limit is given. Our first step with any limit is to substitute the approach value and see what happens. If we can plug it in without an issue, that's our answer. If we plug it in and get 0 over 0, we try factoring or L'Hopital's rule. The third possibility is getting a number over 0. Then we do a sign analysis. That's always the plan. Here, substituting gives 0 over 0, so we must factor or use a L'Hopital. Factoring is way too messy, so we use L'Hopital by differentiating the numerator and denominator separately. After that, we try substituting the approach value again, and when we do, we get 2 as the answer. In this question, a limit is given. Our first step with any limit is to substitute the approach value and see what happens. If we can plug it in without an issue, that's our answer. If we plug it in and get 0 over 0, we try factoring or L'Hopital's rule. The third possibility is getting a number over 0. Then we do a sign analysis. That's always the plan. If we substitute the limit approach value here, we get 1 over 0, so we'll have to do sign analysis. For a sign analysis, we take a value slightly smaller than our approach value and a value slightly greater than it. We substitute them in and look at the results we get. In this case, we get both positive 10,000. It's important that in sign analysis we focus only on the signs. Since both sides gave us a positive, the limit exists and the answer will be positive infinity. If both had been negative, the answer would have been negative infinity. But remember, if the signs were different, then this limit would not exist. In this question, we need the limit as x goes to negative infinity. Infinity can be confusing, so always have a plan. Step 1. Check what type of function it is. If there's no x in the denominator, it's a polynomial. If there is an x in the denominator, it's a rational function. Here we have a polynomial, so we only look at the term with the highest power, which is negative 3x to the power of 3. Now, plug in negative infinity and focus on the sign. A negative raised to the power of 3 stays negative. Then multiply by negative 3, and a negative times a negative gives a positive. So the limit is positive infinity. In this question, we know it's a limit to infinity, so we first determine whether it's a polynomial or a rational function. The difference is that a polynomial does not have an x in the denominator, while a rational function does. So our example is a rational function. To solve it, we always divide everything by the highest power in the denominator. The highest power in the denominator here is x squared, so we divide everything by that and simplify. The next step is to substitute infinity. Everywhere we have a fraction with infinity in the denominator, we replace it with 0, and then we have our answer. No more 2 a.m. doom scrolling on YouTube before a test. Everything's in one spot to help you succeed at Calculus 1 the first time. Let's be honest, I'm not here to convince you of the beauty of calculus. I'm not a professor who can talk for 3 hours about how elegant differentiation is. This is damage control to get you through Calc 1 so you can move on with your degree and with your life. This is your please don't ever make me redo this class again plan. Link in the description. Your future self will thank you. And it's all at a student-friendly price that costs less than a mid-tier restaurant meal. Not even steakhouse level, more like a fancy burger with just one side. See you inside the ebook course.